First of all, thank you all for attending this, and I'm going to try and thrill you with the level of innovation that goes on in what most people would regard as a routine material. So all of the pictures that you see here are actually totally new concepts in steels, and I won't talk about all of them, but I will go through a few of them in some depth so that you get an appreciation of what's involved in design. So for example, this is a slow motion movie, slowed down by a factor of 300, and you see a steel sample that's hitting these granite particles because we've designed a new alloy which has effective grain size of about 0.4 micrometers, and by that I mean a crystallographic grain size. In other words, sometimes when you get textured materials, the actual size is bigger than what you see in a microscope. So the way in which we produce that is really interesting. This outperforms any commercially available material on impact abrasion. That means when you hit the material and you scratch it at the same time. And this work, this movie was taken at the University of Tampere in Finland because they have a very good setup for studying wear of all kinds. And we designed the actual steel, which can be mass produced. All of the objects that I'm showing you can be mass produced. That means thousands and thousands of tons. This is a new shaft that we have created for the large civil engines made by Rolls-Royce. It's a single material here. The conventional way of making these shafts, I'll show you later, is by joining two bits together, because one side has to tolerate high temperatures and the other side has to be able to absorb energy, impact energy. This is a ballistic armor, and I'll explain the basis of that armor later. But this is the world's first bulk nanostructured metal. Again, you can make it in thousands and thousands of tons. And the other kind of threat is a blast. A blast means a sudden distributed load. And this is a new steel that we've created for that purpose, and we are testing it in the laboratory by firing aluminum foil at it at 400 meters per second. And what you watch for is the deflection and the fact that the material shouldn't fail in this. And this I will come to later, but it's a totally new concept in rail steel design. Okay, so with that, I'll begin with pure iron. And pure iron itself has several allotropic forms. That means, a body-centered cubic crystal structure, hexagonal close-packed, and a cubic close-packed crystal structure. At high pressures, epsilon, which has the highest density, is stable. And at high temperatures, we have austenite stable. And then we revert back to ferrite with a body-centered cubic crystal structure. And each one of these has magnetic transitions in it. The most familiar is the ferromagnetic to paramagnetic transition here, but you also have ferromagnetic austenite and antiferromagnetic austenite, and similar transitions in the epsilon iron. And the only reason why body-centered cubic iron is stable under ambient conditions is the ferromagnetism. Okay, so if we do a first principles calculation to see which is the most stable allotrope, and you ignore the magnetism, then the ground state would be hexagonal close-packed, not body-centered cubic. Okay. Now, just imagine a world in which we had iron as a hexagonal close-packed material. It would be very painful because, as hexagonal close-packed systems in general have much fewer slip systems than the cubic forms of iron. And therefore, we would not have the civilization that we know it. You owe the civilization to the magnetic properties of iron. Okay, so that's pure iron, but there's more to it. We are now interested in planets which are much bigger than the Earth, 10 times bigger than the Earth, the so-called exoplanets. And, the core of the Earth contains solid iron, which probably is in the form of the hexagonal close-packed variant. And this has been studied by looking at longitudinal and transverse pressure waves traveling through the core. But when we go to even higher pressures, the first principles calculations indicate that we should revert to austenite at very high pressures, and then to a slightly tetragonal form of ferrite, only slightly tetragonal. Of course, these have not been experimentally verified, although we have some information about the state of the iron in the middle of the Earth. Now, the reason why I'm presenting this is first principles calculations are extremely useful when you cannot do an experiment. So there is no possibility at the moment or even in the distant future of actually knowing what's at the center of the exoplanets. So these calculations are particularly important when we do not have any ability to do experiments, and I'll give you an example in the context of steels later on. Now, between all these allotropes, and there are actually more when you make thin films, between all these allotropes, there are different ways in which you can get solid-state phase transformations. The simplest is a displacive transformation, in which there is absolutely no diffusion, but a physical deformation changes the shape of the unit cell. These are interstitial atoms, and even the interstitial atoms have not moved their relative positions. And there is obviously no composition change at all in such a transformation. But because the atoms move in a coordinated manner, you get this shape deformation, which is really quite large, actually. It's a shear strain of the order of 0.26, which is much, much bigger than a typical elastic strain, which is 10 to the minus 3. So imagine that this is pushing against all the other crystals. Then this will be a strain energy dominated transformation. Many of the features of the transformation product will depend on the accommodation of the strain energy. And there is a second kind of displacive transformation in which the lattice of large atoms is displaced into position, just as over here, but the interstitial atoms are able to partition into places where they are most comfortable. So we have a composition change with respect to interstitial atoms, but all the crystallographic characteristics of a displacive transformation are maintained. And this is when the small atom, we are in a regime of temperature where small atoms are mobile, but large atoms are not. Now, obviously, these are not equilibrium transformations because even these red atoms might want to partition, okay? So not only is there not, the atoms not at equilibrium, but you have this large strain energy term. So these transformations will only happen in certain circumstances, which I'll outline later. And the second mechanism of transformation is what we call a reconstructive transformation. So we start off with the same lattice, but we break all the bonds and rearrange them into the new pattern. And that process requires diffusion. And therefore, you will also get composition changes involving all of the atoms. So I'm going to break up this lattice completely and rearrange the atoms into a different pattern. And in that process, the atoms have reached their most comfortable positions. So you are much, much closer to equilibrium, and there is no macroscopic change in shape. So in other words, there will be a strain energy term due to volume change, but it will be relatively very small. Okay, so what are the conditions that favor a displacive transformation over a reconstructive transformation? Well, there's a very simple equation here. If the velocity of the interface exceeds this term, and this term is effectively the velocity of an atom which moves by diffusion, because d has units of meters squared per second, and lambda is an interatomic spacing, which is meters. So meters squared per second divided by meters gives you a velocity. So this is the diffusion velocity, and this is the interface velocity. So if this is greater than this term, then we get a displacive transformation. And atoms will be trapped either in the product or the parent phase, whether they like it or not. And of course, the complication is that we have two different species here, the large atoms and the small atoms. So this equation could be satisfied for the large atoms, but not necessarily for the small atoms, as I pointed out earlier. But of course, what determines the velocity of the interface? Well, it's the free energy difference between the parent and product phase. So to get a diffusion-less transformation, we not only need slow diffusion, but also a large driving force which wants to push the interface at a high velocity. And there are particular crystallographic criteria which I won't go into today, because those also need to be satisfied to get an interface which is capable of moving fast. Okay, so displacive transmissions like martensite will be far from equilibrium, a huge strain energy, and it's that strain energy which makes them adopt a thin plate shape with a sharp tip, because that accommodates the shape change very nicely. And we will get solute or solvent trapping inside the product phase. Now, if you look at typical steels, not special steels, then there's all these phase transformations that can happen, and they can be classified into displacive and reconstructive transformations. All of these are much closer to equilibrium than all of these. And I'm going to focus for the moment on this transformation, which when I started research was incredibly controversial, so much so that if you looked at a textbook, it would have a paragraph on the transformation and dismissing it basically as being too hot to handle. Okay, so what does it look like? What does bainite look like in an optical microscope? You see the magnification scale there. This is what appears to be a plate of bainite. It actually is very dark compared with the martensite surrounding it. And that immediately indicates that this is not a homogeneous plate. It contains a very large number of interfaces. And that is really strange, because it looks like a nice, neat plate, just like martensite. But if I take one of these and I use transmission electron microscopy, then you'll see that this actually consists of thousands of small plates, like this, where you form a plate, it then stops, and you have to propagate by forming new plates, nucleating new plates. And the size of that small subunit is the same here as at the beginning. In other words, something is happening for these plates to grow rapidly, but they are stopped. And then you have to propagate this collection of plates by forming new plates, nucleating new plates. So this is very important, because if you look at the transformation at a low resolution, and it's important to look at low resolutions, then you will be picking up the growth rate of this object, which includes the time taken for subsequent plates to nucleate, rather than the growth rate of the individual platelet. And we also need to know why they stopped to a limited size before they've met any hard obstacles. So let me first of all show you that this actually results in a shape deformation of the type I described for a displacive transformation. So this is a sample which has been polished organically flat, and we are allowing it to transform to bainite. And you can see that you produce these surface upheavals, which I will show you in the next slide, correspond accurately to the shape change that I described earlier. So this is a real deformation. These transformations not only change the crystal structure, but they also have a physical deformation associated with them. So you can think about them like slip. There is a particular system on which these plates form, a crystallographic system, and the displacements are in a particular direction, but there's a phase transformation at the same time. Now, I explained to you that this is too coarse a scale to observe what's going on, but if you use an atomic force microscope, then you have the resolution to look at individual platelets, and this is a similar experiment done using atomic force microscopy, and you can see the large shear deformation associated with each of the plates. Okay. However, there is something special. austenite adjacent to this plate is also curved. And what's happening is that at the temperatures where bainite forms, you get a plastic relaxation of the adjacent austenite because the strains are too large to accommodate at high temperatures where the parent phase is not strong. So you get this accommodation of the shear deformation, and that partly relieves the strain energy. But there is a consequence of this shape deformation, is that if I look at a transmission electron microscope image of this interface here, you see masses of dislocation tangles both in the austenite and in the ferrite. Now, a displacive transformation requires an interface which can move in a glissile manner. That means glide like ordinary dislocations without interference. If you put obstacles in its way, then it will not move, just like dislocations will not move when you precipitation harden the material. So what happens is that as these subunits grow, you are accumulating dislocation debris at the interface, and once that is large enough, this actually stops. And this problem has been treated quantitatively. And the important thing to note is that the velocity of growth that you measure on an optical scale will be much smaller than the velocity of growth of individual platelets, because there's a time period involved before a subsequent platelet forms. Right, so is there a high-resolution technique in which we can observe the growth of individual subunits? Well, yes, there is. But let me first tell you of another issue which historically appears periodically. Okay, so it started in something like 1930s, where the idea was that, the austenite, the parent austenite, develops carbon-rich and carbon-poor regions, and then the bainitic ferrite forms inside the carbon-depleted regions. So the only way you can get carbon-rich and carbon-poor regions is by a process called spinodal decomposition, and that's illustrated over here. If your solution has a free energy curve like this, then any perturbation of composition will lead to a free increase in free energy. So that's not possible, okay? But if your free energy curve is like this, that means carbon atoms prefer to be next to carbon atoms and iron atoms next to iron atoms, then a perturbation becomes stable. It will grow. So you start off with a homogeneous solution, and you get a composition wave which grows in amplitude. So you need a specific set of thermodynamic functions for the solution for spinodal decomposition to be possible. And Aronson and co-workers proved that austenite does not have this kind of a free energy function. But nevertheless, people argued that, look, you could have a scenario in which the thermodynamics is wrong at low temperatures because equilibrium measurements are usually done at high temperatures. Okay, so we decided to investigate this. And one way you can do this is using diffraction. So we have a sample of steel, which is about 5 millimeters in thickness, inside this inert atmosphere, and there's a annealed platinum wire for reference, and the whole thing is sealed. We then put it into a holder, and this is a synchrotron beam line for powerful X-rays, and these are heaters with which we can austenize and then cool in a controlled way to the Bainite transformation temperature. And synchrotrons basically work by accelerating electrons around a magnetized ring. The electrons bend, and in doing so, they lose some energy as X-rays, and these are funneled down various beam lines located around the synchrotron. So we did this experiment, and the great thing is that you can collect diffraction data as a function of time with a high resolution. So the thing that I want you to notice here is that this austenite peak here started off completely symmetrical, okay, but it ended up highly asymmetrical, indicating that it actually consists of two different peaks with different lattice parameters. Okay, this is the Bainite peak, and this experiment was done at the Grenoble synchrotron. We first did it at the advanced photon source in Arizona, but the resolution wasn't enough. We need high resolution for this experiment. So presenting this data slightly differently, time is progressing along here, and this is the austenite before it transforms. As soon as it starts transforming, you develop these two lattice parameters of austenite. And the reason for this is that the carbon partitioned from the bainite enriches the regions around the bainite, but not away from it. So you end up with two different lattice parameters. But this only happens after transformation. And I'll show you another experiment where we have much longer time before transformation starts at 200 degrees centigrade. And absolutely nothing happens to the austenite before transformation. This is the platinum reference so that we can calculate instrumental broadening and various other things. So you can completely rule out, even at a low temperature of 200 degrees centigrade, that the austenite splits into composition-rich and composition-poor regions, and that the bainite forms in the carbon-depleted regions. Okay, going back to the measurement of the growth rate of an individual platelet, there is a technique known as photoemission electron microscopy at the University of Neustadt in Switzerland, which we used, where you can take a bulk specimen, you can heat it up to whatever temperature you want, austenize it, and you shine ultraviolet light on it, which causes it to emit electrons, which are then collected by the magnetic lenses to form an image in the conventional way. And I'm going to show you a sequence of 4 images using the photoemission electron microscope. And you can see the growth of individual platelets and then other platelets forming, okay? Just as I showed in the transmission electron microscopy. So you can measure the growth rate of individual platelets. And this is the equation that I showed you earlier, but you can use more sophisticated theory to deal with the shape that we have here. And that was developed by Ivansov and Trivedi and so forth. And show that these plates grow 3 orders of magnitude faster than carbon diffusion can happen. Okay? So you should think of bainite as a completely diffusionless transformation product. So how does it differ from martensite? Well, I'll come to that later. But if you argue that this is a diffusionless transformation, you also make various other predictions. And one of those is very interesting. So I'm going to show you a little movie of mechanical twinning happening in indium metal. Indium because, I can recrystallize it at 100 degrees centigrade and reuse it many times, even though it's expensive. This is a piece of indium metal, which I'm going to deform. And when it deforms, it does so by mechanical twinning. And every time a twin forms rapidly, we get an acoustic emission, which I will record with this microphone. Okay, so that crackling sound is because the mechanical twins are forming rapidly. So you generally get mechanical twinning when you deform at a high strain rate or when the material doesn't have sufficient slip systems. Okay, or if the stacking fault energy is right, as in the twinning-induced plasticity steels. So it's an indication of a very high rate of transformation. That rate can be calculated. And these are acoustic emissions recorded by Francisca, one of my postdocs. From bainite transforming, okay? So you, after this work, the acoustic emissions were verified at Delft University in another steel, which transforms at an even higher temperature. So that's consistent. I should look at full screen. Yeah, so the next thing is to look at the chemical composition on a fine scale. And this work I did with Bob Woe, who coined the phrase the atom probe, actually. So he built his own atom probes in our basement. And, in those days, it would take like a week to collect 1,000,000 atoms, whereas nowadays you could do that in a few seconds. But the point is, we hit a bainite-austenite interface. Austenite is on this side and the ferrite on that side, and each dot represents a single atom. And by passing the atoms that you pull out through a time-of-flight mass spectroscope, you can identify what those atoms are and form an image just with those atoms. So here you can see the silicon is uniformly distributed across the interface, but notice the carbon is on one side, okay, in the austenite. So you might think something is not right. We've got a growth rate which doesn't allow carbon diffusion to happen, and yet we can see carbon has partitioned into the austenite. Now, at the time, I happened to be working with a central electricity generating board in Britain on sabbatical, and my task was to define a microstructural change that could be used as a time temperature indicator so that we can assess the remaining life in power station components. And I derived an equation for the chromium concentration of cementite as a function of, all the sort of heat treatments and cycles that turbines go through. And that equation is exactly the same as for describing bainite growing without any diffusion, but partitioning carbon after the event. Okay, so the interesting thing is that the decarburization takes seconds. Okay, depending. This is obviously not 2; it should be 200, 400, and 600. Okay, centigrade. So it takes seconds. So by the time you come to make an observation, the material has tempered itself. Okay, so how can we solve this problem? How can we determine the carbon concentration that exists inside the bainite at the point at which it forms, not as a consequence of tempering because it forms at a higher temperature? Well, this is a free energy curve at a particular temperature for ferrite and austenite. And if you want to find the equilibrium compositions of the two phases, you draw a common tangent here because that gives you equal chemical potentials in both phases. And that defines the equilibrium phase boundaries here and here at that particular temperature. But there is this point which doesn't appear on the phase diagram, where the two phases have identical free energy and chemical composition. Now, what that means is that to the right of that green point, I cannot get diffusion-less transformation because that would raise the free energy. But to the left of that point, it is possible in principle, albeit with a smaller free energy change. So the locus of these points on our phase diagram defines a T0 curve, to the right of which diffusion-less transformation is thermodynamically impossible, and to the left, it is possible in principle. So let's imagine that we form a plate of bainite, but it partitions carbon as it grows. Okay, in other words, it never has excess carbon. In that case, this is the average carbon concentration of my steel. In that case, the reaction will stop when the austenite reaches this phase boundary. The composition of the austenite reaches this phase boundary. Alternatively, if it forms like martensite, but after the growth event, it partitions carbon, then the reaction cannot proceed beyond the T0 curve. Okay, so that defines the thermodynamic limit for that mechanism of transformation. You cannot have diffusionless transformation beyond T0. Okay, so this would form a really clear indicator of whether the transformation happens with the partitioning of carbon, with the ferrite never having an excess of carbon, or subsequent to transformation. And there are now a huge quantity of data to support the idea that the reaction stops at T0. These data were published this year by the group in Sweden. And they represent all these steels, but the T0 curves are all almost identical. You can see from the breadth of these gray lines. So this was published about, I would say, 3 weeks ago, and Google Scholar kindly notified me of this publication. It's a wonderful system, Google Scholar. So I plotted the T0 curves, and you can see that the data fall pretty accurately on the T0 curve. This is simply allowing for strain energy. Okay, so the transformation is diffusionless, but at the temperatures where bainite forms, the carbon escapes into a place where it's more comfortable and eventually precipitates as cementite. Now, if you're designing a strong steel, then cementite is not a good thing to have because it's a relatively hard phase and it will nucleate cleavage cracks. Okay, so we want to stop the reaction here. And you can do that by adding silicon. Now, it's been known for at least a century that in cast iron, when you add silicon, instead of getting cementite, you get graphite. Okay, so the fact has been known for a long time, but we wanted to calculate, how much silicon should we add, because it also has other consequences. Now, the reason why silicon stops the formation of cementite at low temperatures is because the cementite is then forced to absorb the silicon, and it absolutely hates the silicon. Okay, so if you temper, then the silicon will escape, and you will be left with a negligible concentration inside the cementite, too small to make thermodynamic measurements. So even in principle, I can't get the thermodynamic data for silicon in cementite. So this is where first principles calculations come in. You can take your unit cell of cementite, and there are two symmetry positions where you can substitute an iron atom for two different symmetry positions, where you can substitute a silicon atom for an iron atom and calculate the change in energy. So this is pure cementite, and this is with a silicon atom substituted at a particular site, and you can see a massive increase in energy, and similarly at the other site relative to this. So you can then take these data and put them into a thermodynamic package, making gross approximations, because these calculations are done at 0 Kelvin and 0 pressure, really. Okay, so when we do that, we have a handle on how much silicon to add, and you end up with a beautiful structure here with plates of ferrite which are only 1/4 of a micrometer in thickness, separated by these carbon-enriched films of austenite, produced extremely cheaply simply by partitioning carbon. Okay, there's no nickel, nothing necessary there. And it should form a perfect composite because austenite does not have a ductile brittle transition temperature and ferrite is strong. So we made this material, and it had a composition of 3 manganese, about 2 silicon, and 0.4 carbon, 8%. And we tested it, and it had absolutely appalling toughness. Okay, so you can see that the impact transition temperature is well above room temperature. It's totally unacceptable for an engineering application. And we couldn't understand why until we looked at the optical microstructure. Okay, that's important. What's happening is that the T0 curve prevents large regions of carbon-enriched austenite from transforming. The reaction will simply stop. Okay, and there's nothing you can do about that. So you're left with these large blocks of austenite rather than the nice thin films in between. And those transform under the influence of a small stress to untempered high carbon martensite. So it's like designing a beautiful structure inside these collections, but throwing bricks of the size of 50 micrometers inside your structure. So what can we do about this? It's a thermodynamic limit. Okay, let's have a look at that T0 curve again. And this is the average carbon concentration. And let's assume that the ferrite has 0 carbon. Then just by the lever rule, the amount of ferrite I can have is this distance divided by this distance. And I want to increase the amount of ferrite. in order to consume those blocks of austenite. So the amount of ferrite is given by T0 minus the average concentration, and we've taken this to be 0. Now, of course, if I lower the transformation temperature, then I will get an increase in the fraction of ferrite, but there's a limit because of the martensite start temperature. You could reduce X bar, reduce the average carbon concentration, and you would not lose strength because the strength is coming from the bainitic ferrite. But you would consume the blocks of austenite. Or the T0 curve can be shifted to the right by appropriate alloying with substitutional solutes. Okay? So we designed 2 new steels without doing any experiments, one in which we simply halved the average carbon concentration, and the other one in which we shifted the T0 curve to larger concentrations by substituting for manganese. So if you calculate T0 curves, then you can see that the manganese, the nickel T0 curve is located at larger concentrations. And immediately, you get the right microstructure for both of those new steels, and you shift the ductile brittle transition temperature down by 200 degrees centigrade. Okay, so this was the original set of data, and these are the 2 new steels where we have the ductile brittle transition at cryogenic temperatures. And this led to the development of a completely new kind of rail steel. The normal rail steels are based on perlite, and perlite does not, it can have a very high hardness, which is good for wear resistance, but it doesn't have a very high toughness. Whereas the structure that I showed you earlier has a high toughness. So we made a new kind of rail steel. It's in the compositions that I've just illustrated, because it has to be designed for continuous cooling transformation on existing equipment, because the existing equipment is very, very expensive. Okay, so we made it, and the rails were made by British Steel, and they were just remarkable results. Okay, so there are 2 parameters which are really important in rails. One is the wear rate, and this is the only material which reduces the wear rate also on the wheel. Okay, now in Britain we have a crazy system where the rails are actually owned by one company and the rolling stock by various other companies who effectively hire the rails. Okay, so if you improve the rails and you get a deterioration in the wheels, then the customer is not going to be happy. This is the only one in full-scale tests which shows a reduction in the wear rate of the wheel as well. And the second thing is, if you press on a surface, okay, a sphere on a surface, you actually induce a large shear stress under the surface. So every time a wheel goes over the surface, you get a cycle of shear stress under the surface, and that eventually leads to fatigue and a flaking off of material. So these are full-scale tests which were done in Poland, and you can see that our material outperformed anything that exists, and we stopped the test because we were being charged quite a lot for these tests. Okay, a rail is a safety-critical application. You can't simply say, okay, we've got these data, we're going to put them into service. But in the US, there is a test track, where heavy traffic just goes round and round, and the rail was installed there. This is ordinary rail, and this is the new rail, and you can see the level of damage here compared with here after 90 million gross tons of traffic. And the reason for this performance is that the structure we have created doesn't have these hard cementite which ordinary perlite has. In fact, the surface hardens even more because the austenite transforms by this deformation of the rail. And this rail is installed in the channel tunnel. This is an actual picture through the channel tunnel with my rails here. Okay, and in April, I think, or in November 2019, the French sent me a message saying that it has achieved 1 billion gross tons of traffic, okay, without the need for grinding. So every something like 500 million gross tons of traffic, there's a grinder rail which goes to remove fatigue cracks. This has not been necessary. So here you are. This is the bainitic rail and this is the ordinary rail on the same system. Now, the structure that I showed you is very versatile. You can change the scale, okay? We had plates which were 1/4 of a micrometer in thickness. You can make them coarser or finer by controlling the transformation temperature. So there are many variants of that material, and there's even variants which compete with maraging steel, but are much, much cheaper. So this is a plot of fracture toughness versus tensile strength. And we've been working for many years, I think maybe 10 years, with Swiss Steel, who make fasteners, and their sister companies make components for cars. So for example, this is a fuel injector system and made from the carbide-free bainite. So the people we were working with, they simply wanted us to develop code which would allow them to design the steel for their system, and we did that over a period of about 10 years. Okay, so I said to you that we can control the scale of the structure by controlling the transformation temperature. So the question arises, what is the lowest temperature at which you could produce bainite? Well, we have the theory. So we did some calculations for this system and varied the carbon concentration. And as long as the martensite start temperature keeps away from the bainite, you're okay. And what this theory shows, and this is room temperature, is that in principle you could produce this at room temperature. But the kinetics of transformation would take about 100 years, okay? So, you could treat the steel like fine wine and keep it for 100 years and then sell it. But I have yet to find a producer who will agree to invest in that way. So we made the material so that it would transform in 10 days at a temperature of 200 degrees centigrade. And it's a very, very simple composition. Carbon and silicon. We need some hardenability from manganese and chromium to avoid high temperature transformations. When you make a commercial steel, it's not possible to have very low concentrations of impurities like phosphorus. So you need that in order to stop embrittlement at the austenite grain boundaries. So there's a lot of work done by McMahon in the US on temper embrittlement, and the same applies to any strong steel where the structure doesn't cross an austenite grain boundary, because you leave disorder at the austenite grain boundaries where impurities can segregate. So it's a very simple design of material, and this is the optical micrograph here. So it doesn't show anything spectacular, but it is important because it shows that the structure will produce macroscopically isotropic properties. If I now show you a transmission electron micrograph, you will be amazed. So I want you to take a deep breath, okay? And I'll show you the TEM image. Looking at a very, very small region, and these are the very fine plates of bainite. This is 20 nanometers. They are finer than a carbon nanotube, okay? Now, obviously, they are not aligned, as I showed you in the optical micrograph, but these are incredibly fine plates. And we can produce this without any rapid cooling or any deformation. This is simply a phase transformation that happens over a period of 10 days. And these were our calculations of the kinetics of transformation, and these were the measurements. We have impressive properties. You can get up to 2 point something gigapascals of strength and impressive values of toughness as well. And that's what that armor that I showed you, ballistic armor that I showed you at the beginning, is made of. And these are real pictures of the nanostructured bainite being heat treated and produced. And the reason why I want to show you this is that we can produce thousands of tons of this material, right? And my colleagues in China, who translated my book on bainite into Chinese last year, published, have made rolling elements for large bearings, for example, wind turbine bearings, out of this nanostructured bainite. So these are the two characters Fucheng Chang and Zainan Yang, who translated, a 600-page book meticulously. Okay, even the captions, even the legends on figures and so forth. Okay, what I've shown you is an example of design coming entirely from atomistic investigations of the mechanism of transformation. So if anybody asks you why you need all this expensive equipment, are you just having fun pushing buttons? The answer is no. You need that equipment if you want to design new materials. Now, this was the chart that I showed you earlier. And we now have theory to be able to calculate the transformation behavior during cooling as a function of many variables, including chemical composition, cooling rate, the parent structure, and so forth. But microstructure alone is not enough, okay? And the engineer is really not interested. They want properties. So you need a whole bank of methods and experiments to actually design the material. I don't want you to get away with the impression that only the microstructure is relevant. You need all of these techniques, okay? And a good handling of uncertainties, because none of these techniques are actually perfect. You could not design a metallic material simply from any of the models that exist at the moment. So, Stephen Hawking used to say that he has a theory of everything. If I gave him all the variables associated with a particular sample of steel, he couldn't predict a single property of that material, okay? So this is just to emphasize that you need a bank of techniques in order to actually create materials. And I haven't given you examples, but I can talk for a lot longer, but I won't. Now, I mentioned to you that we could, in principle, produce bainite at room temperature, and it would take about 100 years. So we made the material, okay, in 2004, and there's a sample which is polished completely flat so that you would see surface upheavals if transformations happen, and is sealed in a quartz tube containing an inert gas, located in the Science Museum in London. And this experiment should finish in 2104. So it is very unlikely that I'll be around. So you need to tell this story to your children and their children to verify that actually we have produced incredibly fine plates of bainitic ferrite. So I'll stop there, and I'll be very happy to answer questions.
All right, that was a fabulous presentation. So, well, the floor is now open for questions. Anyone with questions, please feel free to unmute and ask questions.
I have a question here.
Please, yes.
Bill Sofa, Harry, nice talk. Thank you very much. What happened? Your bainite, nanostructured bainite, is essentially what traditionally we called upper bainite. And what happened to lower bainite in the traditional sense?
Yeah, so that's a very, very good question. So we have a quantitative model for that. And what that model is based on is essentially that, look, if the time taken for the carbon to partition is long, then you have an opportunity to precipitate inside the ferrite and less precipitation outside. And that would generate lower bainite. But this transformation is slow. It's over a period of, the overall transformation rate is slow over a period of 10 days. So there is an opportunity from the thin plate for the carbon to escape before precipitation can happen. Yeah.
Thank you.
But a very interesting question. I know that I've known you for many years and you haven't worked on bainite as far as I know.
No, but I used to talk to a fellow by the name of Hub Aronson a lot when I was in Pittsburgh.
Right. Say no more. But I acknowledged him. He did some good work on the thermodynamics to show that there isn't any spinodal.
Please unmute. Yeah, go for it, G. Yes.
So, Jima, quick question is, you mentioned briefly about the roles of string energy in this. I'm curious to see if there were, for example, some degree of internal stress or external stress for that matter, how much would you expect this to affect the transformation system in this case?
Yeah, so let me phrase my answer slightly differently. So let's say that the driving force for transformation is of the order of something like 500 joules per mole. Okay, that means the chemical free energy change. The strain energy term accounts for 400 joules per mole if you do a calculation. So Christian developed the Eshelby theory to treat this. And for the sort of shear strain and dilatational strain, the strain energy term itself is 400 joules per mole out of a total driving force of about 500, which makes it dominant in controlling the shape of the transformation product, because a thin plate is the best way to accommodate that strain energy. So it's very large. Does that answer your question?
Yes. So, okay, maybe I can follow up with this question a little bit, right? So then is it viable or possible, for example, if there is, in addition to the internal strain energy that takes place during the transformation process itself, if there is and also, for example, an external stress that's being applied at the same time during transformation? Of course, you wouldn't do this during the steel making itself, but as a curiosity, can you then use this to, for example, change the morphologies or the geometries of these things?
Absolutely right. Very, very good point. So many people have done experiments where you actually transform the material under the influence of an applied stress, and you get a non-random structure developing because some of the plates will have a shape change which accommodates the stress, and those will be thermodynamically favored, whereas those which oppose that stress will not form. So instead of getting 24 different orientations in a particular parent grain, you get those orientations which best comply with the stress if it's uniaxial.
Right.
So it's
right.
a very, very
variance selection. Right. But would that affect also the morphology of the individual, Bainite?
The morphology would be affected because the plates will tend to form parallel. Okay. And that's not a good thing, actually, because you want lots of crystallographic orientations to deflect cracks.
Okay, thank you.
Okay.
Harry, at the beginning of your presentation, you showed an experiment that was investigating the blast behavior of steel plate. I think you might have been collaborating with the same people I collaborate with at Cambridge.
Engineering, right? Vikram.
Yeah, Vikram and Norman Fleck, right? Yeah. So, so in that situation, it's an edge clamp beam, and you're trying to limit the deflection of the beam. And so with the steel that you developed, do you know whether that reduced deflection was just a consequence of its high strength, or was there a change to the strain rate hardening of the steel?
Yeah. So that particular steel is not the one that I've described today. It's actually a very interesting steel, which has a martensitic structure, but it's a very tough martensite because we have reduced the austenite grain size to a ridiculously small level. So the crystallographic grain size becomes incredibly small. And the test that we do in the department, there's only two parameters that we monitor, which is the deflection and to look for any signs of failure. But then the defense people do really large-scale experiments, the bulge with an explosion and so on. And I'm not completely au fait with that, but Vikram would be, I think.
Okay.
Have you done some work on these lines? Or?
Yeah, we did across the scales as well. So the plate tries to find the easiest mechanism to fail, right? It gets this sudden pulse of momentum and it starts moving, and now you have to bring it to rest with the smallest possible deformation. And if you don't have the toughness, then it fractures, and you punched a little piece of metal out from the grips and off it flies, right? So you need the high toughness for sure. But then you're trying to bring a moving, plastically deforming sheet of steel, you're trying to bring its deformation rate to zero as quickly as you can. And so the high strength, right, it gives you the force that essentially brings that mass motion back to zero. So what you were describing is just exactly the way to go. And I've seen work over here, very empirical efforts to try to create so-called blast resistant steels. And what you just discussed actually looks to me to be a very promising route forward.
Yeah, so the motivation for a new concept for very strong steel was that, the nanostructured bainite that I talked about, you cannot weld it, okay? You simply cannot weld it. So it's good for shafts, for bearings, for, armor, but not for anything else. Whereas I think you might have been working on ship steels, right?
We at one point we were, absolutely. And
Yeah.
they have to be weldable, yeah.
So the blast resistant steel is actually weldable.
Yeah.
And we've done all that work.
Oh, maybe it's time to start the project up again.
Okay. I'm not sure whether you could make a ship from it, but...
Me personally, absolutely not.
Okay.
Well, thank you. Any other questions from anyone else?
I have a question.
Yep.
So you mentioned in the iron carbon system, the spinodal is impossible according to Aronson. But then how to explain this carbon composition in homogeneity? Maybe you mentioned it, but I missed it.
Yeah, so there is no carbon segregation before transformation in the parent phase. But when you get a plate of bainite forming and then it partitions carbon, the surrounding region becomes richer in carbon, but not the region away from it in the time scale of the experiment. And that's why you pick up 2 lattice parameters.
I see. Okay.
After transformation.
Mm-hmm. Okay. Next question is steel has been around for many years, as you know, as you worked in this area. Then, what do you see in your view that is the next big thing in steel, or the next promising direction? Is it lightweighting or what?
Well,
what's your opinion? Yeah.
So I get asked this question very many times, okay? And my standard answer is that you have to come up with an idea, okay?
Okay.
So the level of innovation in steels is just enormous. I mean, you can throw graphene out of the window, frankly. The level of innovation in graphene is minuscule compared with what's happening with steels.
Mm-hmm.
And maybe I didn't mention this, but we are using 1.6 trillion kilograms of steel every year. Now, that's not a good thing. That's not a good thing at all because of the CO2 emissions. So if we make better steels, which you can use less of, then you will reduce the CO2 without affecting the quality of life, okay? Mm-hmm. And I'm writing another edition of one of my books, which will have exactly case studies showing you, how you can save steel, real case studies, okay, where buildings have been put up. You can save 22% steel and yet have a cheaper cost overall, So we want to cut down the use of steel. It simply doesn't have any challenges, full stop, okay? So, Elon Musk, his Starship, do you know what it's made of?
I actually watched your videos. Previously people use this carbon thing, but now we switched to steel.
Yeah. So they never used carbon, they used aluminum.
Aluminum, okay.
Yeah, but the Starship is made from austenitic stainless steel. And Charlie Kuhlman, who is the head of materials in SpaceX and also in Tesla, is a very old friend of mine, okay? So I had a long conversation with him where he gave me lots of information on the reasons for selecting steel, okay? I'm going to write that in the new edition of the book. He's provided me with a lot of information. So basically, steel has no challenges, okay? even, you know, when we talk about aircraft, you know, 10% of the aircraft is steel.
Okay, thank you.
Okay. But we've got to cut down the use of steel. Unless you all want to become vegan. That would solve the problem overnight, okay?
Maybe one final question. Anyone else?
I have a quick questions.
Please.
So you mentioned that the carbon depleted from Bainite during the transformation. So did you observe any like lattice parameter change before and after the carbon escape?
Absolutely. So in the synchrotron experiment, we pick up 2 lattice parameters. Yeah. You know, in the carbon-rich regions, actually it'll be more than 2 because there are gradients of carbon, but roughly 2 peaks.
Right. Did you do you roughly remember like what in terms of percentage of what's a percentage of the lattice change due to the carbon
The carbon has a big effect on the lattice parameter.
Mhm.
So typically, you know, for 1 weight % change, you will get a change in the lattice parameter of about 5%. Yeah.
Okay. Thank you.
Okay.
Thank you. Thank you, everybody. Thank you, Professor Vidisha. I think it's been a fabulous evening. Wonderful. With this, let's conclude the event.
Thank you for the invitation. Okay, and goodbye, everybody.
Yes.
Thank you, Harry.
Yes.
Excellent.
Wonderful talk.